The nucleus. Beautiful and mysterious.
But is it really so mysterious? Let's review. Put an electron inside a proton. Spin it around very fast. Faster! There you go. That's better. Now, you have a neutral particle that looks far, but close up, it has a charge distribution. You take that charge distribution, and you can stick a proton on the negative parts. They stick together. You've got deuterium. And now we have tritium that has two neutrons on either side of a proton. One of the electrons tunnels to the center. That creates uncomfortable neighbors. And eventually, the electron tunnels out of the far proton and leaves. And you're left with helium-3, which is stable. So, how does a nucleus work? Well, let's put the proton and the neutron together. There. Now we have deuterium. Do you know how to spell it? But deuterium isn't the most interesting. The most interesting is probably tritium. Tritium has two neutrons surrounding a proton. Now, sometimes tritium emits an electron and becomes helium-3. There we go. Helium-3. But let's go farther. All right. What's this one? Why, it's lithium. Let's use the rule that the protons cannot touch and that the neutrons don't bend very much. They try and keep the protons as far away from each other as possible while still holding on. Now, if we go to 4, we've got beryllium. Beryllium. And in the center of this beryllium, we'll do that later, 5, boron. Now, in the center of the boron, there's a spot. This little spot here where you can put another neutron. That's called the Lagrange point. And then it kind of attaches to the other protons. But it gives you an isotope with +1 neutron. There's carbon. Carbon also has an Lagrange point, so it can also have a +1 isotope. Here's nitrogen. Nitrogen has an interesting property. Up in the upper atmosphere, high energy neutrons come in and can exchange charge with one of the protons. When that happens, you have 3 neutrons in a row, but they can still stay together. It's just not as strong. But what it does do is change the nitrogen into a carbon 14. And that is the radioactive form of carbon that we use to date a lot of organic material. So I'd write it. Carbon 14. There you go. Now, later on, that neutron can emit an electron and change back the nucleus back. There's the electron. It's flying away. And it changes it back to nitrogen. Nice. nitrogen. No, that's nitrogen. Oh, idiot. Anyway, oxygen has two rings that are stacked on top of each other and offset so that the protons don't touch. And each of these rings can hold a Lagrange neutron. That gives oxygen 3, a plus 2, or a plus 1. A plus 1 or plus 2, making it have 2 isotopes. Is that clear? All right, let's draw this in a different way. And draw it as 2 rings sitting on top of each other. I'm going to use a different notation. So plus 1 there, plus 1 in each of those rings. Let's look at fluorine. Now if we keep the same idea that it's 2 stacked rings, then fluorine has a 4 ring and a 5 ring. Now, this is interesting because to mate those 2 rings together destroys the Lagrange points in each of those rings. So fluorine doesn't have any isotopes that are stable because those 2 Lagrange points have been destroyed by their neighboring rings. Like the 4 isn't compatible with the 5. But then you get to neon and you get a 5-5 ring which has 2 Lagrange points. And so you get a plus 2 isotopes. So it really comes down to the number of stable isotopes. And if you go online, you can find isotopes stable of the elements. And if you look at the number, you can see there's a pattern. And that pattern suggests that there's a structure. Not a random amalgam of protons and neutrons, but something more geometric that alternates in some cases. So, the pattern of stable isotopes suggests structure. So, what is the pattern? Well, let's look at the early ones. So we know that boron has a plus 1, carbon has a plus 1, nitrogen has a plus 1, because they're all single ring, and they all have 1 Lagrange point available for a stable isotope. We switch and look at the next set. Oxygen, having 2 rings, has plus 2. But fluorine, because the rings don't mate together evenly, they do connect, but they don't mate evenly, has no stable isotopes. Then back to neon with a symmetric structure, 2. And then sodium with a asymmetrical structure, 0. If we move higher, we can use the same thing for magnesium. And I can't see. Not like that. Interesting. Magnesium, aluminum, silicon, and phosphorus. Magnesium 2, aluminum 0, silicon 2, phosphorus 0. Now we get to sulfur. And sulfur has a plus 3, suggesting that it has 3 Lagrange points available. But chlorine, in this case, would have 1 mismatched ring. And that destroys 1 Lagrange point, but maybe not both. so it has a +1. And you get to argon with a +2. Now, at this point, things become a little confused, and I'm not entirely sure how these work out. It's possible that argon has a mismatched ring and 2 Lagrange points. But then krypton goes back to the +1. And then you can see it's not entirely easy to determine what we're looking at as we go higher. But those have isotopes, and those have many fewer isotopes. More isotopes, fewer isotopes. Few, if any, isotopes. So in the end, the idea is that the nucleus has a structure, and that we can find that structure by looking at the pattern of the stable isotopes. Now from there, it gets a little more complicated.